Welcome, everyone. For today's prep, we're going to see how we can start to apply partial fractions to our integration problems. And it comes down to really four main integrals. So if we can have these memorized, then we'll be well on our way to being able to, once we've done our decomposition, being able to kind of finish off and actually integrate the function that we're interested in. So the first one that I want to start with, well, let's first break these apart. So the first two integrals here, we're going to use these if we have linear terms. So when we do our partial fractions, if we have a linear term and we do the decomposition, we might end up with a single fraction like this, or we might end up with a single fraction where we have a higher power surrounding the entire denominator. So we get these if we have linear terms. The other two integrals here, we're going to end up with these if we have an irreducible quadratic. All right, so let's start with the first one, 1 over kx plus d. So k here is a constant and d is a constant. So this is actually just a k form. One I don't think we've really seen so far, but we're seeing it now. So this is for a k form for log functions. So how does this work? Well, we have this kx plus d in the denominator, so it's just 1 over that term. And when we do the integral, we get the natural log of the absolute value of all that stuff in the denominator, and then we take that constant k that's multiplying just the single power of x, and we flip it and put it in front. So this is kind of like our k forms that we've seen for sine functions and cosines and exponentials, where we have like e to the kx. We integrate the fraction part, or we integrate the main part, and then we take that constant k, flip it, and put it in front. Now, technically, we could prove this. This is actually a u substitution. So what would you do for u? Well, you'd let u equal the kx plus d. And then when you see how the differential works, calculate the differential du, you're going to get k times dx. And if you start to kind of see how the pieces are going to substitute in, the kx plus d is just going to become 1 over u. And we know the integral of 1 over u is natural log u. So that's where the natural log's coming from. And with the differential, we've got a dx, we've got a dx, but we got to do something about that k. So that's where the 1 over k is going to come from. We divide both sides by k. All right, so we're not going to go through all the details there, but this is just a simple u substitution. We're going to see this form enough where you're not going to be expected to go through the u substitution every single time. So just something to have memorized, really. And this is just a k form for a log function. Now, related to this is if we have that same term, kx plus d, but then all raised to the power n. So for this, we can think of this as a k form power rule. And you could prove this if you wanted to, using the exact same substitution. So you'd let u equal the kx plus d. Okay. And when we have a fraction, all with the denominator all raised to an exponent, we would rewrite that with a negative exponent, like we're seeing, so negative n. And if we do our power rule, we keep the stuff that's inside the parentheses, we add 1 to the exponent, and then we take that new exponent, flip it, put it in front. So this is kind of like our standard power rule here, but when our exponent is negative n. And just like before, we would take that k and flip it and put it in front. So it's one of those k form ones. And we would see that, again, from the same thing. The differential, we'd have to get the differential to match. So if this is our u sub, we'd have to divide both sides by k. All right, so let's try out a few examples based on these linear ones that we've seen. and then we'll come back and talk a little bit about the irreducible quadratics here. All right, so let's look at example 1. We want to integrate this function 2x plus 5 over x minus 1 times 3x plus 4. And this is the first example we looked at where we did the partial fraction decomposition. So we're not going to go through the decomposition again. Just go back to your previous set of notes. And what we found after we did that decomposition, so kind of sweeping a lot of work under the rug here, but we did this in a previous example. What we found is that we could rewrite that entire function as 1 over x minus 1 minus 1 over 3x plus 4. All right, so what do we have? We've got two separate fractions now. And both of these are k-form log rules. So both of these are k-form log. So there's no bigger power surrounding our denominator here. All right, so let's use those special rules. So for the first one, this is a k-form. So the constant k in front of the x is just a 1. So when we integrate that fraction, we're going to get natural log absolute value x minus 1. And the k value for this first one, you said, is 1. So we would technically end up with a 1 over 1 in front. So for this first fraction, the k value is 1. So we wouldn't write 1 over 1 in front. Now for the second fraction, what is the k value? Well, the k value for this one, we've got 3 times x plus 4. So the k value is this 3. So when we get the antiderivative for that second term, we're still going to have our minus sign. We're going to get the natural log of the absolute value of all the stuff that's in the denominator, so the 3x plus 4. And then we take that k value, flip it, and put it in front. So we're going to have a 1 over 3 in front. And then finally, plus c at the end. Okay, so that's it. So we're able to identify that both of these integrals were k-form for the natural log, and then the k value is just the number in front of the x. So for this x minus 1, the k value didn't really matter because technically it would just be like a 1 over 1, but the k value mattered for the second one. So we ended up with a 1/3 in front. All right, so let's try another one. So another function we looked at, 1 over x squared plus minus 25, we did the decomposition for that. So again, we're not going to go through the decomposition again. So go back in your notes. But what we found is that we could rewrite that single function as 1 over 10 x minus 5. Make sure I get it right. And then minus 1 over 10 x plus 5. Okay. And so we took this more complicated integral, and we were able to, with our decomposition, we were able to break it apart into two separate fractions. And each of these fractions has a single linear term in the denominator. So there's no bigger power surrounding these denominators. So each of these is going to be a k-form for natural log. And the k value, the number in front of the x for both of these, is just 1. So both of these are k-form for natural log with k equals 1. All right, so we can easily do the antiderivative. And these 1 over 10s that we have, those are just constant multiples. So when we do the integration, we can take that constant multiple and just put it first. Throw it down first. So we have the 1 over 10. And if we kind of think of it as like we're factoring that off, then we're just looking at this fraction 1 over x minus 5. And that integrates to natural log absolute value x minus 5. And then same thing, the 1 over 10 here is a constant multiple, so let's just kind of move that off to the side. We'll put it first. And then the integral of the actual fraction part, 1 over x plus 5, again, that's our k-form. So we're going to get natural log absolute value x plus 5, and then we've got plus c. All right, so far so good. Well, let's look at example 3. And in example 3 here, this is another one we did the decomposition for. So we're not going to re-go through the decomposition, but let's write down what we found. So we found that this function, we could rewrite it after our decomposition as 1 over x plus, just looking off to the side, make sure I'm not getting it incorrect, plus x minus 1 over x squared plus 4. So this was our decomposition. Now what do we have here? Well, this first term is a linear term. So we're going to be able to integrate that. Actually, that's just natural log x. So that one's not too bad. What are we going to do with this second fraction, though? Well, we're actually going to break it apart further. So we've got our one linear fraction here, but it's this fraction we're going to have to do a little bit more work with. And we're going to break this apart even further. So what do we get? What do we get? Well, we're still going to have that 1 over x. And when we have this fraction, each term in the numerator, we're going to think of dividing that by our denominator. So we're going to get a fraction for just the x over x squared plus 4, and then we're going to get a fraction for just the 1 over x squared plus 4. And why we have to do this is because each of these separate fractions is going to integrate differently. So we've still got the 1 over x, but now we've kind of broken that one big fraction apart based on the numerator. And now we're going to see how to handle each of these integrals. So let's go back and back to our list here of important integrals. And we see that when we have those irreducible quadratic terms, if we split apart, so normally for irreducible quadratics, we end up with ax plus b over our x squared plus a squared. And our strategy is going to be to break apart the fraction just like we did. And one of the terms is going to have an x in the numerator, and the other one is going to have a constant, just a constant. All right, so what happens with the fraction that has the x? Well, if this is the case, then we could prove this formula. So I have what the integral here is. It's 1/2 natural log, the stuff in the denominator. So you could prove this with a u substitution. So you'd let u equal the x squared plus a squared. A squared is just a constant. So when we calculate our differential, we get the 2x dx. And we're not going to go through everything, but you can see we've got our u term that's going to be in the denominator. And then if we start to think about our differentials, we've got our x dx, and we've got an x dx in our main integral. So the only thing we would have to do is divide by 2. So that's where this 1/2 is coming from. All right, so for the terms with an x over the x squared plus a squared, we end up with 1/2 natural log absolute value x squared plus a squared as our antiderivative. Now, the other case where it's just a constant, this ends up involving our inverse tan function, arctan. And we have to look at, in order to get this antiderivative, we have to look at this constant. So whatever constant we have, it's going to be positive. And we're going to do the square root. And that's the value that gets kind of plugged in two places into this formula. So let's read through it. The integral of 1 over x squared plus a squared is 1 over a times inverse tan of x over a. So we take whatever number is part of our denominator there in our irreducible quadratic, we do the square root of it, and that's what we end up with here. Now this one might seem kind of, where does this come from? We've actually seen this before. So this is one of our basic antiderivatives, actually. We're just kind of generalizing it a little bit further. So if we recall, we had a basic antiderivative. There's a special case of this that we'd seen where it was 1 over x squared plus 1. And the special case said that this was just inverse tan of x. So the a value in this case is just 1. So really what we're ending up with is a 1 over 1 with x over 1 if we do the square root of that constant. So this is something we've seen before. Now we're just generalizing it a little bit where if we have plus a positive number here, well, we do the square root of that number and we flip it. Again, you could prove this with a u substitution. All right, so let's put this to use. So if we go down to example 3, we've done the heavy lifting. We've done the original decomposition. So that was our main work that we did before. We went a little further and broke that one apart. So now we're ready to get our antiderivative. So for that first fraction, that one's just a nice linear term. So natural log absolute value x. Then for the x over x squared plus 4, this is the format, this is the irreducible form where we have an x in the numerator. So this is going to be the natural log of the absolute value of our denominator, so x squared plus 4, and then we get a 1/2 in front. And the 1/2, again, comes from the kind of like the exponent here after we do the derivative and we have to do our u sub and all that. So again, this is going to be a common enough type integral where at this point you can just write down, just know what it is. And so finally for our last integral, this is the one where we have just a constant in the numerator. So we're going to end up with, well, minus because we're subtracting, and this is the one that involves arctan, so inverse tan. And what is the number that we're going to kind of flip and put inside our inverse tan function? Well, the constant here is 4, so we're going to put in the square root of that. So we're going to put in 2. So x over 2, and then it also gets a 1 over 2 in front. So that 2 that we're seeing in both places is the square root of that 4. So we're kind of seeing that in 2 spots. All right. So if this was, if this was something complicated like a 9, well, that's actually, that's not complicated. But then we'd have a 1 over 3 and a 1 over 3. All right. And then finally, just throw on the usual. We're doing an indefinite integral, so plus c out at the end. All right. So this is the idea. And, we'll try some more examples of this, and we'll look at a couple more complicated type integrals later on as part of this note. So we'll see you then. Bye-bye.